Okay, so for this session, week 0 recap of organic chemistry, Chem 1 and A with Farhat, we're gonna go over what organic chemistry is. We're gonna go over a review of the atomic structure with protons and neutrons in the nucleus, and then electrons, specifically valence electrons, which are the electrons on the outermost shell. Uh, Simple Lewis structures and how to draw them with practice. um the different types of bonding, like ionic versus covalent bonding, and there's two types of covalent bonding. There's non-polar covalent bonding and polar covalent bonding, depending on the difference in electronegativity. Hybridization, like sp3, sp2, sp orbitals, their bond angle, their electron geometry, and their orbital shapes. Bonding with valence bond theory, Vesper, sp2 hybridization and orbital overlaps, types of bonds, orbital diagrams. So this is all like very similar together. Sp hybridization scheme, and then at the very end, he started going over structure of organic molecules and reactivity, like nucleophiles versus electrophiles, and that's gonna start to get into more old chem stuff. But basically, this is a review of Gen Chem. Okay, so let's first start with section 1, organic chemistry. So organic chemistry, you can think of it as the chemistry of carbon, right? And specifically carbon and hydrogens, because organic molecules will have carbons and hydrogens, right? Um, any other atom, right? Any other atom that is not carbon or hydrogen is going to be called a heteroatom. Heteroatom. So hetero meaning different, atom meaning an atom like carbon or hydrogen. So a heteroatom is going to be an atom that is not a carbon or hydrogen. It's going to be different than a carbon or hydrogen, like that. And some examples of that would be like fluorine, chlorine, bromine, iodine. These are the halogens specifically on group 7A of the periodic table. There's also going to be oxygen, nitrogen, or sulfur. So these are like the most common heteroatoms that you're going to see in organic chemistry. Okay. Okay. So now let's move on to a sneak peek of what you're going to be learning in organic chemistry, right? So let's say I have this structure here. And do you know the name of the structure from, let's say, Gen Chem? Like the name of this ion? What's the name of this ion right here?
Hydrogen monoxide?
Hydrogen monoxide would be something else with one oxygen. There is one oxygen, right? Monoxide, and there is hydrogen right here. But we call this right here hydroxide.
Oh,
Hydroxide ion.
hydroxide.
Hydroxide ion, right? hmm And a hydroxide ion is going to have a -1 formal charge like that. Okay. Um, and then let's say we have this structure here, where we have a carbon bonded to 3 hydrogens and an iodine, like that. Do you remember? It's okay if you don't, just let me know, and then I could go over it. But the partial charge of, let's say, this carbon and the partial charge of this iodine, depending on the difference in electronegativity between those two atoms.
I think the partial charge on iodine, since I think it's like more further to the
hmm
right, so it'd be partial negative on the iodine
hmm
and partial positive on the carbon.
Correct. It's going to be partial negative on the iodine and partial positive on the carbon, because iodine is more electronegative, like you said. It's more on the right and, oh, like more on the right on the periodic table. So because it's more electronegative, think of it as like a tug of war, right? This bond here has 2 electrons. This iodine here, since it has a higher electronegativity than carbon, it's stronger than the carbon. That means that it's gonna pull the electrons towards itself more. And the charge of electrons is a negative charge. So because iodine is gaining more electrons, it's gaining more negative charge. That's why iodine is partial negative. And because carbon is losing electrons, it's losing negative charge, meaning that it's gaining positive charge. That's why carbon is partial positive charge, like that. Okay. Now, I'm gonna just go over the terms nucleophile and electrophile right now. So nucleophile, and it's going to be abbreviated as Nu with a negative charge like that, and electrophile. Okay, and that's going to be abbreviated as a capital E positive charge. Okay, so when you see nucleophile, you could think of it as a lover of the nucleus, right? Lover of the nucleus, right? Because nucleo is nucleus, phile is the lover of. And in Gen Chem, we learned that the nucleus is consisted of protons and neutrons. So
Mm-hmm.
overall, the nucleus is going to be positively charged. And an electrophile, you could think of that as the lover of electrons, right? Because electro is going to be electron, phile is the lover of, so electrophile is the lover of electrons. And electrons are negatively charged. So you know how opposite charges attract, like negative charges are attracted to positive charges?
Mm-hmm.
If nucleophiles love positive charges, what charge do you think nucleophiles are if they want to attract a positive charge?
Negative.
Negative charge, that's right. So that's why nucleophiles will be negative charge, like either a partial negative charge or a full negative charge like that. Okay? Same for electrophile. If an electrophile wants to attract a negative charge, what charge would the electrophile have?
Positive.
Positive, correct. So based on these structures here, let's look at this hydroxide ion first. Do you think this hydroxide ion is a nucleophile or an electrophile based on what charge it has?
Nucleophile.
Nucleophile, correct, because it has a full negative charge right there. Now let's focus on this carbon here of this structure. Is this carbon a nucleophile or an electrophile?
Electrophile.
Electrophile, correct, because it has a full positive charge right there, right? Now, this iodine here is technically negatively charged, right? But we're not going to consider that as a nucleophile in this reaction because this is going to be a good leaving group, which I'm going to go over later. So before we go over that though, in organic chemistry, right, nucleophile is going to attack an electrophile, right? And what that means is that a nucleophile with electrons is going to like use the electrons to attack an electrophile, make a bond with the electrophile right there, like that, right? It's never the other way around. Like sometimes, like people in 118B or 118C, they make the mistake of having an electrophile attack a nucleophile, but that never happens, right? This doesn't happen. Electrophile would never attack a nucleophile. So another way you could think about it is like this. Um, Negative charge, attack positive charge. Nucleophile, attack electrophile. Okay. Okay. So let's go back to here. An example would be like this. Let's say this OH minus here is going to attack this electrophile. And what that means is that this oxygen here with two electrons, right? This is a lone pair of electrons. That lone pair of electrons, like this right here is a curved arrow. And what a curved arrow means is that it's going to show the movement of electrons. This lone pair of electrons here is going to move and make a bond to that carbon right there. So this oxygen here is trying to make a bond with that carbon right there, right? And let's say that the oxygen and carbon is now connected. There's a big problem on this carbon, right? This carbon will have 5 bonds. That's way too many bonds, right? Because you know the octet rule, an atom wants to have 8 electrons,
Mm-hmm.
which is like 4 bonds. This carbon is gonna have 2, 4, 6, 8, 10 electrons. So to conserve the octet rule, we're gonna have to kick out a good leaving group. And this iodine here is a good leaving group because it can handle a negative charge. It's very electronegative. It's one of the halogens, right? On the period 7, like column 7. So what we're gonna do is that we're gonna use the 2 electrons in this bond right here to kick it onto that iodine, and this is gonna be our new structure right here. Okay, where this iodine here, it got kicked out and it's now negatively charged. Before, this iodine had 3 pairs of electrons, but it gained this extra pair of electrons from this bond right here. The 2 electrons from this bond went onto this iodine, which is now here, giving this iodine a negative charge, like that. Right? And then this oxygen OH right here, like on the new structure, is from this hydroxide ion right here. Right? This right here is the new bond between the oxygen and hydrogen and carbon. And that new bond has two electrons. Those two electrons are these two electrons right here.
Mm.
Mhm. Any questions on that, Amanda, before we move on? Like how this hydroxide ion attacked this molecule and kicked out this iodine to get this alcohol and this I minus ion?
Um,
This will definitely be shown up again at the end of medicine A, but Ferry had just showed it here at the beginning to give you a sneak peek, right? But
mhm.
it's okay if you don't understand it right now because this won't be tested on the first midterm. This is just a review of what you will be learning in medicine A, right? So anything that does not make sense, Amanda?
I think I understand
Uh-huh.
it.
Okay, okay, that's good. Um, so now let's move on to the next section, which is atomic structure and valence electrons. Okay. Atomic structure and valence electrons. So an atom will have a nucleus which has protons and neutrons. Protons are positively charged, neutrons are neutral. And they're going to have electron shells. And do you remember how many electrons max are going to be in the first energy shell, first energy level?
One.
One. So it's going to be two
Oh,
electrons for the
two.
first.
Yeah,
Mhm.
two.
Two electrons, and then the second one would be eight electrons. And so this is the first energy shell right here. The
Hmm.
maximum amount of electrons it could hold is going to be two electrons. This is the second energy shell right here. The maximum amount of electrons that it could hold is going to be eight electrons. One, two, three, four, five, six, seven, eight. And the same as for the third electron shell. The maximum it could hold is eight electrons. Okay. So let's say that's one, two, one, two, three, four. So the first energy shell is already filled up. It's occupied by two electrons. The second energy shell has four electrons, right? One, two, three, four. And because it's on the outermost shell, right? Like the shell that has, like it's on the outermost shell, like the farthest away from the nucleus, we call these the valence electrons, right? Valence electron, valence electrons, valence electron, valence electron. Okay. And these valence electrons are very important because these valence electrons will make the bonds, like polar covalent bonds or non-polar covalent bonds in organic structures. Okay. Um, so let me pull up a periodic table for you right here. Okay. Do you remember how we can calculate the number of valence electrons by looking at the periodic table?
Yes, the group number,
Mm-hmm.
but not the transition metals.
Correct. The group number, not the transition metals. So this is 1A, this is 2A. We skip the transition metals, moving on to 3A. This is 4A, and then 5A, 6A, 7A, and noble gases 8A. So how many valence electrons would nitrogen have?
Five.
Correct, because nitrogen is on the group, fifth column, so it has five valence electrons. Nice. Okay. So now we're gonna move on to the simple Lewis structures. Simple Lewis structures. And this is just a way of us showing how atoms bond to each other. So if we look at the lecture slide, and we look at, let's say, ammonia, which is NH3. This nitrogen here wants to have an octet, 8 electrons. So this nitrogen here with 3 hydrogens attached to it, we have a pair of electrons, a lone pair of electrons right there. And are you familiar with drawing out a Lewis structure based on the condensed form like this, Amanda?
Yeah, you first draw
Mm-hmm.
the skeleton.
Mm-hmm.
So it'd be like N and then with three H's around it with the
Mm-hmm.
line
Right? H. And
or or
what does
without
the
the
line
line.
represent?
That because the line represents a single bond.
Mm-hmm. Correct. A
And
single
so
bond?
that's already 6
Mhm.
electrons
Yes.
and there's 8 total, I think. So
Mm-hmm.
the two dots go on top of the N.
Yes, because we want the nitrogen to fulfill the octet rule.
Mm-hmm.
So we put the 2 dots to represent that lone pair of electrons to have the nitrogen have 8 electrons, right? And how did you figure out we needed 8 electrons in total?
Um, I add the valence
Mm-hmm.
electrons from N and the three H's.
Mm-hmm. Correct. N has 5 valence electrons. H has 1 valence electron, but because there's 3 H's, 3 times 1 is 3. So that we add them together, 5 plus 3 is 8 valence electrons. And to confirm that we have 8 electrons in the structure, each bond represents 2 electrons. So this is 2, 4, 6. And then this lone pair has 2 electrons, so 8. So that's good. Nice. Um, Let me give you 3 more examples, Amanda, and I want you to walk me through how you would draw the Lewis structures for these. 4, um, C2H4, CO2, and then last one, HCN. Okay, let's start with CH4.
Okay, so CH4,
Mhm,
we first draw the where each thing would be. So C with 4 H's around it.
mhm,
And then for the valence electrons, there's 4 plus 4 is 8.
mhm,
The lines, and then that's it.
correct. Because carbon has 4 valence electrons, hydrogen has 1 valence electron, but there's 4 of them, so 4 times 1 is 4. Add them together, that's 8. We have 4 bonds, so 2, 4, 6, 8. That's it. That's good. And just a challenge. Do you know the name of this structure? It's okay if you don't. This is like later on, but have you learned about the name nomenclature of this molecule?
Pentane?
So very close, right? Because it is an alkane, which the ane at the end shows that it's an alkane. But if you look at the suffix, I mean the prefix, pent, how many numbers do you
Oh,
think
pent
that
is
goes with?
5.
That's 5, right? That's
Um,
5. How many carbons do you see here?
4.
Oh,
What?
4 hydrogens, but 1 carbon. 1 carbon.
1 carbon.
hmm And the prefix for 1 carbon is meth. Does that sound familiar?
Oh, yeah, yeah, yeah.
hmm So this right here would be meth. Wait. Methane? Methane? Yeah, wait. Let me make sure. Let me make sure. Methane. Just in case. Methane. Yeah, methane is CH4. Correct. Because one is meth. Two, three, four, five, six. Let's go down here. Right here. One is meth. And then I want you to try out these all the way through 10. What so you already got 5, which is pent.
Mm-hmm.
Now try 2, 3, 4, 6, 7, 8, 9, 10. You haven't seen this yet, but just let me know if you don't
6 is
know this.
hexane.
Hex. Yes, hex. And we're not putting ane because it could
Oh,
be
yeah,
ene,
just the hex.
hexene or hexine, depending on if
Yeah.
it's an alkene or alkyne. Mhm.
Um, oh, I think either 3 or 4 is butte.
Four will be built.
Oh, four.
Mm-hmm. Mm-hmm.
Uh,
Eight, think
Eight, it's
of
oct.
oct, correct, correct. And then everything else is a little bit tricky. So I could
Yeah.
just go over that with you because like I think the more like straightforward way is like the pent for like pentagon five,
Yeah.
and six like hexagon,
And
so hex,
octagon.
and oct for octagon eight. Yeah, everything else is tricky, right?
Mm-hmm.
So two is F, three is prop, seven is hept, nine is known, 10 is deck.
Mm.
hmm So this will be very important for nomenclature later on. There's also 11 and 12, but I forgot that. But he will go over that. And when you send me the lecture slides next week or week two, we'll go over that when he goes over that. Okay.
Okay.
Okay. So now try C2H4, glue structure.
Mm. Okay. I'm pretty sure it's the structure is like H, C, C, H with two H's on the bottom.
hmm
And then,
and then if you try it, you could send it to me like on Discord, like a screenshot of it if you have an iPad, or if you could take a picture of it on paper and send it to my Discord so I could see your work.
okay.
Uh-huh. Okay. Yes, that is correct. Another way that you could draw it is this right here, which could be a little bit more accurate because electrons, there are negative charges, and like charges, would they attract each other or repel each other?
Repel.
Repel, right. So electrons want to be far away from each other as possible, right? So to make them far away as possible, we could draw it in this orientation right here. What you drew is not wrong, it's correct still. But this one here would be more accurate to show like the bond angle between these bonds, right? Which like, do you remember what the geometric shape of this carbon, the hybridization and the bond angle of this carbon right here? Like you can start with the hybridization. Is it sp, sp2, or sp3? We haven't gone over this yet, but I just want to see where you're at, Amanda.
Let's see.
hmm
For just the carbon,
This carbon right here.
um, I think it's SP.
So sp is going to have two bonding groups, right? So let me just give you a big summary, and then later on I'll explain it more in detail. The difference between sp, sp2, and sp3. So sp is going to have two bonding groups, and I'm gonna abbreviate bonding group as bg. sp2 is going to have three bonding groups. sp3 is going to have four bonding groups. So if you look at this carbon right here, this
Mhm.
carbon has one, two, three bonding
So
groups.
SP2.
Yes, sp2. That carbon would be sp2. Um,
I wasn't sure because there's only one pi bond.
there's one pi bond, correct, which is this double bond right here. And we'll go over what pi bonds and sigma bonds are later. Um, but this double bond here counts as one bonding group. hmm So what would be the bond angle here for this sp2 carbon?
Um, 109.5.
So 109.5 would be tetrahedral for sp3, sp3,
Oh,
sp3 carbon, right? So this right here would be 120 degree apart. And the geometric shape of a 120-degree molecule is trigonal planar. Does this sound familiar, Amanda?
yeah.
That's good. That's good. Okay. And I'll go over the 109.5 and 180-degree shapes after, but let's finish off these two Lewis structures here. CO2.
Okay.
Mhm. Yes, correct. And I like how you showed your work of counting the valence electrons. Carbon has 4, and then oxygen has 6, but since there's two of them, that's going to be 12. Add them together, that's 16. And you drew it correctly, where carbon is going to be in the middle. And then the two oxygens will have two lone pairs of electrons each, which will add up to 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. That's good. Nice. And because this carbon here has two bonding groups, right? 1, 2, it's going to be sp hybridized. So this carbon here is sp hybridized, and the bond angle between that is 180 degrees. Like this is 180 degrees right there, right?
Yeah.
And then that, because it's 180 degrees away from each other, is going to be a linear electronic geometry shape. Linear. Okay, nice. Let's try the last one, HCN. What other classes are you taking this quarter, Amanda?
Um, Math
Mm-hmm.
21D,
Oh wow, 21D.
Physics 9B,
Uh-huh.
and Engineering 6.
Oh my gosh. And for OChem, for your major, do you only have to go up to 118B or do you have to take
It's up to
118C?
just to be.
Just to be, okay, okay. That's good.
Uh,
Mhm.
okay, I think I did this right.
Mm-hmm. That is correct.
Yeah.
Mm-hmm. Nice, 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 Amanda. 1 plus 4 plus 5 is 10. And then you drew it correctly, which is going to be like this. And carbon here in the middle is still sp hybridized because there's two bonding groups, right? 1, 2. Bond angle between those two bonds is going to be 180 degree, which is also going to be linear. Okay?
Okay.
Okay. So now let's move on to the next section, which is going to be ionic versus covalent bonding. Okay. Okay. Ionic versus covalent bonding. Okay. Okay. So let's first talk about ionic bonding. So metals are usually going to be on the left side of the periodic table, and non-metals are usually going to be on the right side of the periodic table. Right? So let's have this periodic table here. Like these right here are metals, right? Like sodium, um,
Potassium.
potassium, magnesium, calcium, right? Um, on the right side are going to be non-metals like boron, carbon, nitrogen, oxygen, and the halogens, fluorine, chlorine, bromine, iodine, right? So generally, right, if we look at the periodic table, which one will have more valence electrons? Metals or non-metals? Which one will have more valence electrons?
Non-metals.
Non-metals, correct, because it's more on the right side of the periodic table, right? And you know how atoms are going to be happy if their outer electron shell is filled up, it's full, like full orbital.
Mm-hmm.
Let's say we have sodium here, which has one valence electron, and we have chlorine here, which is a halogen on the seventh column, seventh group, which has seven valence electrons. So 1, 2, 3, 4, 5, 6, 7. So do you remember ionization energy from general chemistry?
Not really.
That's okay, that's okay. So ionization energy is how much energy needed to remove a valence electron, right? So we see that this sodium here has one valence electron. And that one valence electron, based on sodium's atomic number, which is 11, right? Let's say this is sodium right here, and then this are its valence electron shells. That's the first one, that's the second one, this is the third one. We said earlier, the first valence electron has a maximum of 2 electrons. So let's draw those 2 electrons in the first energy level, 1, 2. And that means that we used up 2 of sodium's 11 electrons. So it has 9 electrons left. The second energy shell has a maximum of 8 electrons. It could hold 8 electrons. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So that's 10 electrons we used up so far. Sodium has one more electron because that's 11. That one electron is going to be at the third energy shell right there, right? So what do you think is going to be easier to make this sodium atom happy? Do you think it would be easier to add 7 electrons to this third energy shell, or would it be easier to remove that electron to
It would
um,
be easier
have
to remove the
mhm,
one electron.
correct? And because it would be easier to move that one valence electron here, do you think sodium will have high or low ionization energy? Like
Low.
low, yes, correct. Low IE ionization energy because sodium wants to get rid of that electron. Now, if you look at chlorine here, chlorine has 7 valence electrons. Do you think it would be easier to remove all 7 valence electrons or add an electron to that outermost shell?
Easier to add an electron.
Easier to add an electron. So would the IE or ionization energy of this chlorine be high or low?
High.
High, right. High IE. That's why in his notes, Fahrenheit's notes, non-metals NM will have high ionization energies, and metals M will have low ionization energies, right? Because metals want to lose their electron, non-metals want to like keep their electrons and gain an electron, right? Now, we can make a bond between the sodium and chlorine because this sodium here can actually move its one electron to that chlorine right there. And the reason why I drew out a single hook arrow instead of a double hook arrow is because a single hook arrow here represents the movement of one electron.
Mm. Oh, and the regular one was showing like the movement of like the whole bond or like
The
two
whole bond
electrons.
or lone pair of electrons.
Yeah.
Right. Because a bond has 2 electrons, or you can move a lone pair of electrons, which is also 2 electrons. So that full regular bond is the movement of 2 electrons. Right. Mm-hmm. Correct. And then after that, right, we would have a sodium with no electrons on its third energy shell anymore, making it positively charged. And chlorine, because it gained an electron, would be negatively charged, like that. Right. And this is an ionic bond where a full positive charge is attracted to a full negative charge. They're gonna float around each other like that because opposite charges attract. Right. Okay. In, let's say, air, right, not in aqueous solution, NaCl is going to be salt, table salt,
Yeah.
right? But if you put it in water, H2O, the NaCl will dissolve into ions, Na plus ions and Cl minus ions, right? And the reason why is because the chemical formula or Lewis structure of H2O or water is this right here, where we know the oxygen is partial negative charge and the hydrogen is partial positive charge because oxygen is more electronegative than hydrogen. So oxygen is going to withdraw or pull electrons from the hydrogen. And because of that, right, there are a lot of H2O molecules in the solution. The Na plus is going to be surrounded by the oxygens of the water, right? Which is going to be partial negative charges. And all of these oxygens here will have hydrogens, like hydrogen, 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 HH, 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 like that, right? Whereas the chlorine here is going to be surrounded by the hydrogens of the water, right? And these hydrogens here are going to be part of a water molecule. And I'm drawing one of it out like that. Like this is one H2O molecule here. But all of these hydrogens will be part of any H2O molecule like that. And we know that these H's are partial positive charge, which is why they're attracted to this negative charge on the chlorine like that. Right? So that's why in aqueous solution or water, NaCl will break apart into ions, sodium ions and chloride ions. Right? In like let's say air, there's no water around, so these two structures here will be salt. It's solid. It's solid like that. Okay. Okay. So now let's go on to covalent bonding, where instead of like having one atom completely donate an electron to another atom, those two atoms are going to share, like share electrons, right? So let's say, for example, we have water, H2O. H, O, H. Hydrogen has one electron, so it has one valence electron. Oxygen has 6 valence electrons because it's on the 6th column, 6th group. We see that oxygen is missing 2 electrons to fulfill the octet role. So what can happen is that one of the hydrogens with 1 electron can come close to this oxygen right here and make a single bond with that oxygen like that. The other hydrogen can come close and make a single bond with that oxygen by sharing those electrons. And that's a win-win for both atoms because now the oxygen has an octet role. It has 8 electrons. 2, 4, 6, 8. That's good. Hydrogen here has 2 electrons, which fulfills the first energy level because the first energy level has a maximum of 2 electrons. So the hydrogen is also happy like that, right? So we could redraw this in bond line structure or Lewis structure like this, right? Where this bond here represents this set of electrons, this bond right here represents that set of electrons like that. Okay. Okay. So, like we said, with CH4, right? These hydrogens have 1 valence electron. Carbon has 4 valence electrons. 1, 2, 3, 4. These non-metals here can share electrons to have this carbon have an octet rule, right? 8 electrons, 2, 4, 6, 8. And all of these hydrogens here will have 2 electrons, right? 2 electrons, 2 electrons, 2 electrons, 2 electrons, like that.
Mm.
And then we could draw that out like this. Where each bond has 2 electrons, and those 2 electrons are here, like that. Right? But this bond is different than this bond, right? Like they're both covalent bonds, but one is polar and one is nonpolar. So
CH4 is nonpolar.
CH4 is nonpolar because the difference in electronegativity between carbon and hydrogen is not big enough for it to be polar. There's no partial charges, right? There's no partial positive charge, there's no partial negative charge. But oxygen is very electronegative. It's like it has a high electronegativity. So if you take the difference between the oxygen electronegativity and hydrogen electronegativity, it's big enough to have a partial negative charge on oxygen and a partial positive charge on hydrogen like that. Okay? Um, and then Farhat uses these ranges. So use these ranges in his exams, right? Covalent bond, aka non-polar covalent bond, right? Covalent bond, non-polar, right? Where the difference is not that big, is going to be a difference, which is this delta symbol, En electronegativity of less than 0.5. A polar covalent bond is going to have a difference in electronegativity of between 0.5 to 1.7. And an ionic bond, difference in electronegativity is going to be greater than 1.7, right? An ionic bond, the electrons are not shared, right? One atom completely gives up its electrons, and another atom takes that electron. They're not sharing the electrons. Covalent bonding means that they're sharing electrons. But the polar covalent bond is not sharing equally, right? Nonpolar is sharing the electrons equally. Okay. And you will be given a periodic table with the electronegativity values on the exam, right? So you could use those values to find the difference and then figure out if it's a non-polar covalent bond, a polar covalent bond, or an ionic bond, right? Okay. Do you know the most electronegative atom in the periodic table?
Fluorine.
Fluorine, correct. Um, do you know why the noble gases, the eighth group has no electronegativity?
No, I don't think
Uh-huh.
so.
Yeah, it's because the noble gases, the eighth group, right? How many valence electrons does it have?
All eight?
All eight. So does that mean that it's happy or
It's
angry?
happy. It
It's
doesn't need
happy.
to
It
do
doesn't need
bond.
anymore. Correct. So that's why it has a electronegativity of zero because it's happy. It doesn't want to grab an electron.
Oh,
hmm Whereas fluorine, how many valence electrons does fluorine have?
7.
Seven. So it really wants to grab one electron to be happy, right? It just needs one more electron to be happy. So that's why it's very electronegative, right? But do you know why fluorine is more electronegative than the atom below it, which is chlorine?
Um,
Think about the atom size.
oh, I think um as you go down the periodic table,
hmm
it gets bigger
It
and
gets bigger,
further
correct.
away from the nucleus. The electrons are further away from the nucleus.
Electrons are further away from the nucleus, correct. And also think of it as polarizability, where let's say fluorine, right, has seven electrons, and chlorine has seven valence electrons as well. Um, the fluorine here, because it's a smaller atom, the valence electrons has less space to move around, to float around, to breathe, less breathing room. Whereas chlorine, it's bigger than fluorine, so the electrons have more room, more space to breathe. That's why it's more stable. And because it's more stable, it's less angry, less electronegative, right? Okay, that's good. Okay. A way that you can think about electronegativity strength is like this. Electronegativity will increase going up and going to the right,
Hmm.
right? Or you can think of it like this, diagonally, like that. The electronegativity will increase that way. But these ones here are not electronegative because they're already happy with 8 electrons, like that. Where fluorine is the most electronegative atom, like that, right there. Okay. Okay. Now let's move on to the next section, which is going to be um hybridization. Okay. Hybridization, orbitals, sp, sp2, sp3, ammonia bonding. Okay, practice, formation, sp2, sp2 overlaps, types of bonds, sigma bond, pi bond, sp hybridization, sp overlaps. Okay. 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 So we're now going to talk about sp versus sp2 versus sp3 hybridization. So if we look at carbon here, the most important atom in organic chemistry, it has four valence electrons because it's at the fourth column, fourth group. And back in Gen Chem, these are the atomic orbitals. And how would you go about filling these atomic orbitals if carbon has four valence electrons here? Like, how would you fill these orbitals in order?
Mm, I think I would put one arrow on each thing until I filled in
hmm
all the spots I can.
Yeah, one at a time, right? One S has t- two spots, so two there, that's four. So, oh wait. We don't fill out two S yet because think of one S, right, as this is the first energy level, and think of 2s and 2p together is going to be the second energy level. And we said the first energy level has a maximum of 2 electrons, and the second energy level has a maximum of 8 electrons, right? 2, 4, 6, 8 electrons.
Mm-hmm.
So we already filled up the first energy level. Now when we move on to the second energy level, based on I think Hund's rule, we have to like
Yeah.
keep going until it fills up all of it halfway, and then we could fill up the other one fully, like that, right?
Every orbital in a sublevel is singly occupied before any orbital is doubly occupied.
Mm-hmm. Correct. Correct. Right.
Okay.
Mm-hmm.
So
So,
we fill in the first energy and then we move on to the second energy.
and when we move on to the second energy, we fill up one electron at a time, like one here, and the next one would not go here, right? The next one will go on to here, and then if we had more valence electrons, it will go here, here, and then once that's all full, then we fill in the other half, the second half, like that, right? So let's say we have what's the ninth atom? Let's see here. Ninth. Fluorine. Let's say we have fluorine, right? How would you fill out um fluorine's um orbitals, atomic orbitals, if you were given this fluorine? Let's see.
Fluorine
Mhm.
was the one that has 7.
It will
Uh,
be nine. Oh, it's on the seventh group, but it has nine. Oh wait, actually, yeah. It has seven valence electrons. You're correct. You're correct. Yeah.
okay.
Yeah.
So I put um
Mhm.
the 2 arrows in one S,
Mhm.
and then 1 and 2S,
Mhm.
3 and 2P. So that's 1, 2, 3,
Like this in this
5,
order.
6. Yeah.
Uh-huh.
And then the last arrow will go in 2S.
Correct, like that. And that would be the atomic orbital of fluorine, like that, right? Now let's do carbon. Let's go back to carbon. How would you do carbon?
Um, 2 arrows on one S,
Mm-hmm.
1 on 2S,
Mm-hmm.
and 1 on 2P.
Yes, like this, right?
Yeah.
Correct. Okay. Mm. Oh, wait. Ignore what I just said here, where that's the second energy level and that's the first energy level, right? Because all of this here will be in the second energy level. Because on the second energy level, there will be 4 valence electrons, and these are the 4 valence electrons right here, like that, right? Um, So these 4 electrons that we just drew out is the second energy level, not the first energy level.
Oh,
Hmm. Right? Now, what we're gonna do here, wait, let me see. Wait. I need to double check something really quick.
okay.
6, let's see, plus 4 electrons and carbon. Okay. Orbitals. 1s. Yeah, 2s, 2p. First initial level. 2, 4, 6. Oh, okay. So what we did here was we just fill out the valence electrons, but when we fill out atomic orbitals, we have to fill out all of the electrons, right? So carbon, if you look at the periodic table, it has 6 electrons because it's the sixth atom right here, right? So we have to fill out all 6 like this. 1, 2, that's the first energy level. This one right here is the second energy level, right? But since we already used up 2 electrons, there's 4 more. So that's 1, 2, 3. Wait. 1, 2, 3, 4. Like that. Did that make sense, Amanda? After this, we could try out fluorine, right? Because like what we went over earlier was incorrect, but this one here is correct. So we have to fill up the 1s first, and then the 2s, and then the 2p.
Oh,
Um,
yeah.
mhm, right. That's why when I said fluorine has 9, right? 9 electrons. Let's
That's
fill
the
out.
atomic number.
Mhm, right. It's based on the atomic number, not the valence electrons. Okay. So now practice with fluorine. Yeah, that is 2, 4, 6, 8, 9. And the order that you did it was you fill up the 1s first, and then you fill up the 2s, right? You don't go 2s and then you skip to 2p like that. You go fill up 2s first, and then you fill up the 2p halfway, right? So we used up 1, 2, 3, 4, 5, 6, 7. There's two more. 8, 9. Did you do it in that same order? Yes, that's correct. That's correct. So this atomic orbital here is going to be based on the atomic number 9, 9 electrons, right? Where 1s is the first energy level, and then this is going to be the second energy level. Okay. But now we're going to talk about combining the outermost shell together. So if we look at carbon, for example, again, which is over here, these right here are the valence electrons of carbon, right? These 4 electrons right here are the valence electrons because it's on the 4th group. And these 4 electrons here, 1, 2, 3, 4, are on the second energy level, the outermost shell. And we said earlier that these valence electrons are going to be the ones that are going to make the bond, right? So if how many s orbitals do you see here in 2s? There's one s
One.
orbital, right? How about how many p orbitals do you see here in 2p?
Um, two.
1, 2,
Two.
and 3. 3 right here. So there would be
Yeah.
3, right? This is 1, this is 2, and this is 3, right? There's 3 p or 2 p orbitals right there, right? Okay. And in total, right, there's gonna be 4 orbitals in the second energy level. 1, 2, 3, 4, like that, right? So if you combined the s and p orbital, that's gonna be I'm gonna do it like this right here. This is 1s, and these are the 3p. So s, p, p, p. If you have an sp3 hybrid orbital, you're gonna combine all of these together and merge it into one, right? But you're gonna use 1, 2, 3, 4 orbitals to do that. So if an atom is sp3 hybridized, they're gonna have 4 sp3 hybrid orbitals, right? If an atom is sp2 hybridized, that means that we're combining these 3 orbitals together, right? 1s and 2p orbitals together to create this sp2, right? And because there's 3 of them, 1, 2, 3, that's going to be 3 sp2 orbitals plus 1 unhybridized p orbital, which is this one unhybridized p orbital right there, right? Now, if something is sp hybridized, that's going to be 2 because we're only combining s and p right there like that, plus 2 p orbitals right here, like that, because we didn't combine these 2 p orbitals there, right? Does that make sense so far, Amanda? Any questions on this?
Um,
Mhm.
for the SPPP, is that like
Mhm.
the energy levels we just did?
Yeah, these SPPP here is going to be this SP P, P, P here.
Oh, okay.
Yeah, I'm just showing it out in this form here, which is the second or the outermost energy shell, right? It could be the second or third. But I'm just showing it because these outermost ones are very important for bonding. Those are the valence electrons, right? And the shape of an s orbital is a sphere. The shape for a p orbital is going to be dumbbell shape like that, right? The shape for sp3, sp2, and sp orbitals are going to be degenerate like this, where there's one small orbit and there's one big orbit like that. And the p orbital is going to be still be a dumbbell shape like that, right? So if you have an sp3 hybridized atom, to get that sp3 hybridized atom, you have to combine all of these orbitals together, which is 4 in total, right? 1, 2, 3, 4. That's why you have 4 sp3. sp2 combines 3. 1, 2, 3. That's why you have 3 sp2 plus 1 unhybridized p orbital right there. If you have sp, you're combining 2 orbitals, 1 s and 1 p, to get 2 sp hybridized orbitals and 2 unhybridized p orbitals, like that. Right? Okay. Okay. Did that make sense, Amanda?
Yeah.
Mhm. Okay. So now let's go over CH4 methane. This CH4 carbon here has 4 bonding groups. 1, 2, 3, 4. Meaning that it's going to be what hybridization? sp, sp2, or sp3?
SP3.
sp3, correct. sp3. So how many sp3 orbitals would this carbon have if it is sp3 hybridized? Would it be 3 or 2 sp3 orbitals?
Mm, 3.
Mhm. So if we are sp3, right, we're gonna have four sp3
Oh,
hybridized
4.
orbitals, right? And
Yeah.
the reason why we need 4 is because um you know how we have one s right here and 3p. To get sp3 combined or hybridized, we're gonna have to combine them, combine all 4 orbitals together like that, right? Hydrogen here is going to be considered an s orbital because it only has one valence electron, right? So I'm gonna draw it out like this, where this carbon here has 4 sp3 orbitals like this. 1 is there, 2 is there, 3 is there, and then the fourth one is there, like that. The green orbitals I drew out are the sp3 orbitals. And then I'm gonna draw hydrogens out like this, where the size or the shape of the s orbital is a circle, a sphere, like that, right? And then because carbon has 4 valence electrons, I'm gonna draw it out like this. 1, 2, 3, 4. Those 4 red electrons right there are going to be the valence electrons of carbon. I'm going to draw the valence electrons of hydrogen in purple like this, where this is 1, 2, 3, 4, like that, right? Okay. So this head on overlap right here is going to be the bond, the single bond, right? The sigma bond, right? So that's going to be called the sigma bond. And this sigma bond here is specifically between an s orbital and an sp3 orbital, right? These green orbitals here are sp3 orbitals, and this blue here is an s orbital, like that, right? Okay. And the geometric shape of this is going to be tetrahedral, right? Meaning that bond angle between them is going to be 109.5 degrees, like that. Okay. Okay. So now if
Or
we, yeah, and,
3.
uh-huh.
It's SP3 is like the max. It's like all 4 of the
Mm-hmm. Yeah, and
things.
there's four sp3 orbitals. This is one sp3 orbital right here.
Mm-hmm.
Um, this is the second sp3 orbital right here. This is the third sp3 orbital right here, and then this is the fourth sp3 orbital right there. That's why I said there's four sp3 orbitals on that carbon right there, like that.
Okay.
Mm-hmm. Okay. And then these pink highlighted bonds right here that I just highlighted out is gonna be these single bonds right here, like that. Right. Okay. Okay. So I'm gonna quickly go over sp2 and sp orbitals, and then we can finish off the rest next week. And if you have any questions, text me. I'll send you the recording of this and our notes to Discord as well. But I'm gonna go over this, and then we can finish off next week. Like finish off the last part of this week. Okay. So let's say
Mhm.
we have this structure right here, which is called ethine. Eth meaning there's two carbons, ine meaning there's a triple bond, alkyne. Because this carbon here has three bonding groups, 1, 2, 3, that carbon is going to be sp2 hybridized, right? And when an atom is sp2 hybridized, remember how when we talked about like combining these atomic orbitals together, if something is sp2 hybridized, there's going to be three of them because we're combining, to get sp2, we're combining one s orbital with two p orbitals. So this is one, S, two,
Oh.
three. That's why we're combining those three right there, like, right? Because to
Uh-huh.
get sp2, we need one s and two p's. And then how many is that? One, two, three. So that's why we get three sp2 orbitals,
Okay,
right?
it's finally like clicking.
Uh-huh. That's good. That's good. And if you look at sp3, right? Like if we go backward, um, to get sp3, we need one s and how many p orbitals? Three p orbitals, which is one, two, three. Combine all of them together, that's four, four sp3 orbitals, like that. Now, if you look at sp, right? How many s orbitals do we need to combine to make sp?
1,
One. How many p orbitals do we need to get sp?
1,
One. Combining these two in total is
2.
two. That's why we get two sp orbitals.
Mm,
And how many unhybridized p orbitals do we have here that did not hybridize at all?
2.
Two. That's why we get two unhybridized orbitals when we have two sp orbitals. Now let's look at sp2. How many s orbitals for sp2?
Um, 1,
One. How many p orbitals for sp2?
2,
Two. Right? How many in total?
3,
Three, right? So when something is sp2, there's three sp2 orbitals. How many unhybridized p orbitals? How many p orbitals did not hybridize?
1.
Which is this one right here, right? Okay, so now this carbon here, since it's sp2, how many sp2 orbitals does this carbon have? This one right here.
3,
Yes, three. How many unhybridized p orbitals?
1.
Yes. Same as for this carbon right here. That carbon is also sp2 hybridized, and there's three of them, and there's one p orbital. Does that make sense so far, Amanda?
Yeah.
Okay, so now I'm gonna color code this. I'm gonna color code the sp2 as green, and I'm gonna color code the p orbital as purple. Do you remember the shape of an sp2 orbital, Amanda?
Um, that one was like it was like a sphere and it was like half a
Mm-hmm.
dumbbell with a sphere.
Right, right, right. So I'm gonna draw that out like this. So let's say that carbon is this carbon right here, and I'm gonna draw its three sp3 orbitals like this. That's one sp2 orbital.
Mm-hmm.
This right here is the second sp2 orbital. How many sp2 orbitals do we have left to draw?
1.
One, correct, right here. I'm gonna draw the other carbon out like that. Same thing. One sp2 orbital there, second sp2 orbital there, the last sp2 orbital over there. Okay, does that make sense so far, Amanda?
Yeah.
Okay, now I'm gonna draw out the hydrogens out like this, And hydrogen is going to be S hybridized, right? And S shape is a sphere, like that. Sphere, 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 and sphere. Does that make sense so far, Amanda?
Mm-hmm.
Okay, so now this carbon here has one p orbital, like we said, one unhybridized p orbital, which is a dumbbell shape, like that. This carbon also has an unhybridized p orbital, which is a dumbbell shape, like that. And you know how these two p orbitals are parallel to each other? Like they're like side by side, like that?
Mm-hmm.
That is called a pi bond. That's the pi bond right there, which is a bond, right? And I'm gonna draw out the valence electrons of carbons here. Like this is like, let's say 1, 2, 3, 4. And this carbon here also has 1, 2, 3, 4. Hydrogens has 1, so I'm gonna draw that in purple. 1, 1, 1, 1. I'm gonna highlight the sigma bonds in pink. This is a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. And I'm gonna highlight that here. That's a sigma bond pink, sigma bond, sigma bond, sigma bond, sigma bond. In purple, well, let's do red. Say in red, that's the double bond, which is a pi bond. And that pi bond right there is coming from this parallel overlap right here, like this. Does that make sense so far, Amanda?
Yeah.
Uh-huh. So this double bond here has one sigma bond, which is that pink bond, and one pi bond, which is that red bond right there. Okay. Now, you know how this double bond here is parallel overlap? Double bonds cannot do free rotation. Like if we try to rotate this, right, we would break the parallel overlap between these orbitals and there would no longer be a double bond, right? They have to be parallel. We can't rotate it. But if you look at the previous example, we can rotate like this bond right here, which is this bond. Like we can rotate it because this is a head-on overlap. Like they're connected like that, which can rotate like that,
Mm-hmm.
right? And they're still connected like that. Okay. And this right here is going to be trigonal planar if it's sp2, and the bond degree between them is 120 degree, like that. Okay. Now let's move on to ethine. What is the hybridization of this carbon here, Amanda?
Um,
How many bonding groups does it have?
mm, 4.
It has 4 bonds, correct? 1, 2, 3, 4. But it will have 2 bonding groups. This is one bonding group. This is the second bonding group.
Oh.
Hmm. Right. And with 2 bonding groups, it's going to be sp hybridized,
Mm-hmm.
right? And if we said if something's sp hybridized, how many sp hybrid orbitals would there be?
2.
2, correct. So let's draw out this carbon's 2 sp orbitals. 1, 2. How many unhybridized p orbitals would that carbon have if there's 2 sp hybridized orbitals?
2.
Yes, 2. And I'm gonna draw that out like this. One is gonna be vertically, like up and down, like that. The second one is gonna be horizontal, like this. I'm gonna do the same for the other carbon. The other carbon is also sp hybridized, which has 2 sp orbitals. One here, second one there. It also has 2 unhybridized p orbitals. One here and one here. Okay, and I'm gonna draw out the hydrogens right here. Hydrogen, hydrogen, which is s hybridized, s, s, and then draw out the valence electrons like that. Valence electron, valence electron, valence electron, valence electron, valence electron, right? And this right here is going to be bonding to each other, the vertical p orbitals, and then these right here horizontally are going to be bonding each other like that. So I'm going to highlight the sigma bonds. This is a sigma bond. This is a sigma bond. This is a sigma bond. Um, and then I want to highlight the pi bonds, right? This is the pi bond. This is the pi bond. So I'm gonna highlight that in this structure. This is a sigma bond, the head-on overlap, like they're directly touching each other. This is a sigma bond. One of it is a sigma bond, right in the middle. And then these two bonds here of the alkyne are the pi bonds. They're parallel to each other, right? So a triple bond, right, will have one pi bond and I mean one sigma bond and two pi bonds, right? A triple bond will have one sigma bond and two pi bonds, like that. Okay. Does that make sense, Amanda?
Yeah.
Okay. So sigma bonds or pi bonds, which one do you think is stronger? A stronger bond?
Sigma.
Sigma, right? Because they're directly touching each other. They're like on each other like this, right? But a pi bond is weaker because they're not touching each other directly. They're just parallel to each other, right? But if you compare, let's say, a single bond versus a double bond versus a triple bond, which one is the strongest?
Triple bond?
Triple bond, right? And that's because it has more bonds. It has one sigma bond plus two pi bonds. Whereas a single bond only has one pi single bond, sigma bond, and then the double bond has one sigma bond and one pi bond, like that, right? So that is gonna be 180 degrees apart, linear, for sp hybridized. Now let's talk about the single versus double versus triple bond. We said the single bond has one sigma bond, double bond has one sigma bond, and triple bond has one sigma bond. But double bond also has one pi bond, triple bond has two pi bonds. So if we think about the strength, right? The strength is going to increase from single to triple bond, where triple bond is the strongest. And then if we think about length, right? Length would increase from uh triple bond to single bond. The shorter the bond length, the stronger it is. So triple bond is the shortest because if the bond is very strong, they're gonna pull the atoms closer and closer and closer together, making the bond very short. But if the bond is weak, like a single bond, the bond is gonna be long, right? Because the atoms are gonna be farther away from each other. So a way that you can think about that is that strength and length of the bond is inversely related. Like they're opposite from each other, right? So the stronger the bond, the shorter the bond, right? Okay. So I know that was a lot, Amanda, but I'll send you the recording so you could rewatch this. Send you the notes as well, and then next week we'll move on to chapter two, the last part of this week's lecture. Any questions, Amanda?
No question.
No questions? Okay, that's good. That's good. I hope this helps. And I'll see you next week, Amanda.
Thank you.
Of course. Bye.